Today in class we worked on task 8.6, fireworks, where we continued working with projectile motion problems. In today's task we compared key features of the paths of different types of fireworks. In the Ready section of tonight's homework, you're going to be graphing the quadratic functions and identifying the key features, including the increasing interval, decreasing interval, the vertex, and the x and y intercepts. In this example, which is number 1 from your workbook, we're given the function f of x equals x minus 3 times x plus 1. First, we're going to identify the x-intercepts. We know that the x-intercepts have y values of 0. It's where our function crosses the x-axis. If we take each of our linear factors and set them equal to 0 using the zero product property and inverse operations, we can solve for x, and we find that our x values are 3 and negative 1. So our x-intercepts are located at negative 1, 0, and positive 3, 0. Our vertex is obtained by taking the average of our x values from our x-intercepts. So if we add our x values, the 3 and the negative 1, from our x-intercepts and divide those by 2, we get 1. That 1 represents the x value of our vertex. Next, we take the x value and place it in for the x variables in our original function. When we do that and simplify, we find that f of x, or f of 1, is negative 4. That is the y value of our vertex. Therefore, our vertex is located at 1, negative 4. When we multiply our linear factors back together and simplify, we end up with x squared minus 2x minus 3. That tells us that our y-intercept is located at 0, negative 3. That's where our function crosses the y-axis. From there, we know that our function is symmetrical, and our axis of symmetry is also located where our x value of our vertex is, which is at positive 1. So with our y-intercept being 1 unit away to the left of our vertex at 0, if we go the other direction 1 unit to positive 2, it's going to have the same y value. And from there we can graph our quadratic. Here's another example. We know that our y-intercept is 0. When we look at our quadratic function of ax squared plus bx plus c, we know that our c, or our constant term, represents our y-intercept. Because we don't have one, it's understood to be 0. Next, we'll factor our quadratic. Our greatest common factor of x squared and 6x is x. When we factor the x out from each of the terms, we're left with x times x plus 6. We set each of our linear factors equal to 0 using the zero product property. And by using inverse operations, we solve for solve for x. So we get x equals 0 and x equals negative 6. Those are our x-intercepts. The first one located at negative 6, 0, and the other one is located at 0, 0. We know that the x-coordinate of our vertex is located halfway between those 2 points, which would be at negative 3. And again, if we substitute that x value back into our function and simplify, we'll get our y value of our vertex, which is -9. So our vertex is located at -3, -9. -3 is also our axis of symmetry. If we expand that graph so that you can see it a little clearer, we can also see that we have a point at -5, -5, and -1, -5. Again, for any point, we can simply replace our x values of our function with the x value that we want to plot. So if we want to plot -5, we can substitute the x's with -5 and simplify to get our y value. Same thing for -1. If x is -1 and we replace our x values with -1 and simplify our function, we get -1, -5. In the Ready section, we were identifying the key features of the quadratic functions. And in the Set section, we're going to be interpreting those key features. So we're going to make sense of those key features of the quadratic function in the context of the story. So when we look at this first function, d of t equals -50 t squared plus 400t, we see that we have our exponential term and our linear term, but we don't have a constant term, which means it's 0. So we know that the y-intercept is 0. It's starting at the surface if this is in context and we're talking about gravity and velocity. So the first thing that we want to do in order to identify the key features with this function is to factor it out. So we're looking for the greatest common factor of these two terms. We know that we can factor out a -50 from each of the terms. And when we do that, we're left with the two linear factors, -50t times t minus 8. Next, we're going to set each of those equal to 0 using the zero product property. And through inverse operations, we're going to solve for the variable t in each. We end up with t equals 0 and t equals 8. So in the question, when will the ball hit the ground? If this were, we're throwing the ball up in the air and then it's coming back towards the ground. We're throwing it up in the air at a velocity of 400, and the acceleration due to gravity is -50. The ball will hit the ground after t seconds, or whatever our unit of measurement is. We know that the ball will reach a maximum height, which is our vertex, at 4, when the time is 4 seconds. We know that because our two x-intercepts were 0 and 8, and we know that the x value of our maximum, or our vertex, is located halfway between those 2 points, which is 4. When we substitute that back in for the t variables and simplify, we end up with 800. That is our maximum height. So our vertex, or our maximum, on a graph would be located at 4, 800. 4 is the time that it takes for the ball to reach the maximum height, and 800 is the height. Here's another example. We know that the first term, which is our exponential term, represents the acceleration due to gravity. We know that the second term in our quadratic function, which is the linear term, represents our velocity, and we know that the third term in our quadratic function, which is the constant, represents our initial height. In the Go section, we are reviewing parallel and perpendicular lines in systems of equations. So we're identifying whether the given linear functions will generate parallel lines, perpendicular lines, or just intersecting lines. Remember that parallel lines are lines that have the same slope. Perpendicular lines have opposite reciprocal slopes, so their slopes are opposite signs, and their slopes are also the reciprocal of the other. So if we flip the fraction upside down, that's the reciprocal. And then intersecting lines just have different slopes. Additionally, on the parallel lines, remember they have the same slope, but they would have different y-intercepts. So they're crossing the y-axis at different points, but they're rising and running, rising and running, rising and running at the same rate, which means that they are never going to touch. In this first example, as in all the examples, the first thing that we need to do is to make sure that both of the equations are in slope-intercept form. So we need to isolate the y variable using inverse operations. We're going to subtract 2x from each side of the equation, which leaves us with negative 18y equals negative 2x plus 36. And then we're going to divide each of the terms, or each complete side of the equation, by negative 18. And we're left with y equals 1/9 x minus 2. We can see that when we compare the slopes, the slope of the first equation is negative, the slope of the second equation is positive, so they are opposites. The slope of the first equation is 9, or 9 over 1, and the slope of the second equation is 1 over 9, or 1/9, which is the reciprocal of 9. So they are opposite and they are reciprocal, which means they are perpendicular lines.